Hello. Um, I always don't know what to say at first when I start the camera because it's kind of weird sitting here talking to myself. So I guess I'll just start like I normally would in class. Usually I just start writing things and then you guys do the same. I know Chapter 5 is titled Applications of Derivatives, which to me, when I hear that, I think, awesome, we're going to do some real world stuff. But that's not really the case for the first few sections anyway. It doesn't look like it's really going to get good till later on. So here we go. Usually I write myself my own notes before class, and then I use my notes to give to you guys. I have not done that. Well, I was hoping this video is going to work a little better. I have this iPad set up on some books. I might have to start over. I don't want to start over because I don't have that awkward beginning again. See if I can get this thing up a little higher so that that's a little better. I'll just have to pay attention to that. So anyway, here we go. Extreme values of functions. So the first thing we're going to talk about, like I was saying, I don't have my own notes written, so if I pause for a long time, it's because I'm looking in the book, thinking of what I'm going to say next. And I feel really sick all of a sudden, so I'm not really feeling like doing this, but once I leave school today, I won't have internet, so I got to get it done. Let's see here. Extreme values of functions. Yeah. First thing we're talking about is absolute extreme values. This has more than one name. It's also called an extreme values. Extreme meaning, I'm doing a horrible job right now. Hopefully there's no one else in the room watching this. It's just you guys. You'd be making fun of me. I should probably start over, but I'm not going to. Alright, anyway, so here we go. Let's say we have a graph, any old graph of anything. A parabola is a good one. The extreme values for this, it has no maximum, but it has a minimum right here. On my graph, it looks like that's about y equals 1 or so. I don't know. Extreme values just means maximums and minimums. Absolute extreme values means like the highest point or the lowest point on the graph. That's basically what it means. These could also be called you could call it absolute, minimum or maximum, or it's also called global minimum or maximum. That means the same thing. I mean, you think a global is like the whole world. Well, this is like everywhere on the graph, the minimum and the maximum. So don't be confused. Or you could just call it the minimum or maximum. It doesn't matter. It all means the same thing. And the way you find these, like my parabola example, if I'm just looking at the whole graph, if the domain is all real numbers, then it's got a global minimum right here at y equals 1. Or you wouldn't say y equals 1, you'd just say the global minimum is 1 when x equals 1 or whatever. There's a good example in your book. If you look at page 192, it's got a parabola, and it does a whole bunch of examples. Like, if you just do the regular old parabola, if you want to find the absolute max and min over the whole domain, oops, you can't read what I'm writing over here. So if you want to find the absolute minimum and maximum over the whole domain, well, there is no maximum because it goes up forever. But the minimum, the absolute minimum, would be 0 when x equals 0. Alright, because that's the lowest it ever gets. I'm going to again try to make this thing higher. Let's try this. Oh, yeah. It's better. Okay, but if you restrict the domain that you're looking at, you could change your maximum and minimum. For example, they take, okay, here's a parabola. Now let's restrict the domain to from 0 to 2 is what they do in the first one. So everything from here to here, that's all you're looking at. Well, now you do have an absolute max. And that absolute max, if I plug in 2, let's see, that would be 4. The absolute max would be 4 when x equals 2. And the absolute min would be 0 again when x equals 0. Easy enough. The part where it gets weird is if you restrict your domain in such a way where it's this is called a closed interval. That's when we restrict it to everything including 0, everything from 0 to 2 including 0 and 2. That's inclusive. If you restrict it and it doesn't include those, like if we go from 0 to 2 with the parentheses, that means it doesn't include 0 and it doesn't include 2. Then there's actually no absolute maximum or minimum. There's neither. Because all you'd be looking at is from here with an open circle to here with an open circle. And you might think, well, there is too a minimum, you know, it's right there. It's right when I get to the lowest point. But couldn't you always go a little lower? Like you can't include 0, so your lowest point would be 0.00000001. Well, and if you wanted to go lower, you just add another 0.0, you know, whatever. Like there's no absolute maximum because the highest point would be, oh, it's 3.9. Well, no, then you could go 3.99, then 3.999. There is no absolute maximum. You can always just add a 9 on the end and go a little higher. So that leads to theorem, what they call theorem 1 in the book, the extreme value theorem. I don't know why I switched to pencil here. Extreme value theorem. Make sure you can actually see this stuff. Which basically says that your function has to be continuous on a closed interval A to B. Then it'll have a maximum and a minimum in that interval. I'm not going to write that all out. I don't think you really need to either. But just know that in order for there to be an absolute max and min, the interval needs to be closed. Because if it's open, then, like I said, you can always go a little higher, a little lower. So that's absolute max and min. That's like looking at the whole graph, or global. And I just realized I'm doing hand gestures and you can't see those. So that's not really working. So then, now there's also, not only is there absolute maximum min or global maximum min, there's also, let's see, I might just need to get new paper. There's also local max and min, maximum and minimum. these could also be called relative max and relative min. Those mean the same thing. And this is basically just looking at a section of the graph and figuring out the maximum and minimum. So they got a good picture there that's something like this. And then it goes down. And it's like, well, if you restrict the domain to like just here and just look at this section here, well then this is a relative maximum. If you're just looking around this section, that would be a relative minimum. This would be a relative maximum here if you're just looking at this section. And the absolute minimum and maximum, well the absolute minimum would be down here. That's the lowest point overall in the graph. And the absolute maximum would be here. So that's the difference there. Absolute and global mean the same thing. Keep that in mind. Local, relative mean the same. I don't know why they have to have two words for that. You think you could just stick to one. That's all it means. Let's see. What's next? So now we're going to figure out how to find these maximums and minimums. I might have to switch videos though, because 7th period's about to start. Can go a little longer. So I mean, you can kind of see that. Let's look at, for example, right here. That's a relative max or a local maximum, and what happens here? I mean, I guess I can't really ask questions. You're not going to respond. Well, what happens here is it goes up and then it turns around. It has to turn around. That's what makes it a maximum. And what happens when things turn around? Hey, the tangent line, the slope of the tangent line is 0, which means the derivative is equal to 0 at that point. Same down here at your local minimum here. It turns around. Hey, slope of the tangent line equals equal to 0. So the derivative equals 0. So basically, if you got a function, if you could find where the derivative equals 0, that point, that x, that's where your local maximum or local minimum will be. And there's a way you're going to have to be able to check. Also, so we could have the derivative equal to 0. That's one place you could get these maximums and minimums. Also, something like this, they did that on purpose, how it kind of, it's a curve, and then it stops, and then it comes down. Well, what happens right there? What's the derivative? If you remember from, I don't know, I think it was chapter 3 when we were doing derivatives, the derivative doesn't exist at that point, right? There's a doink, there's a corner, or we said doink, or there were some other names. But so if the derivative doesn't exist, we might have a local maximum or minimum. So we're going to I'm just going to kind of make a little list of places where maximum or minimums might occur. We could have, like, for maximums or mins, so to find max and mins, it could be where the derivative equals 0. It could be where the derivative does not exist. Does not exist. And then also, the third way is at endpoints. As long as they're included in the domain, right? As long as it's a closed interval. Like here, that was the absolute minimum. You know, that's an endpoint. As long as that's included in my domain, we're okay. That was a relative max. That's where the slope was equal, or the derivative was equal to 0. relative min, derivative is equal to 0. Here's an absolute max. Well, that's where the derivative does not exist. And then here's a relative minimum. That's just where it's an endpoint. So those are the three things we're going to look for when we're doing these. So now I think I'm going to do some example problems for you, show you how to find these extreme values. It's an exciting thing, let me tell you what. But 7th period starts in 2 minutes, so you'll have to switch to the next video because I'm going to stop this and make the next one after class. Okay, so see you in an hour, but to you it'll feel more like 10 seconds because you just got to click the next video.